Alright, so in today's video we're going to talk about electrical load calculations. Before we do that, we need to discuss the basic electrical formulas and the units used in electrical systems. Then we will discuss the difference between a single phase and three-phase circuits and the relevant formulas for each of those different type of systems. Then we'll discuss the typical voltage, phase, Hertz used in the US and Canada, which is where I'm from, and there's different voltages, phases, and Hertz that are used in other countries, which I'll kind of briefly discuss. The NEC code regulations on calculating electrical demand for residential and commercial buildings I will go over. So there's different calculation methods for determining the electrical demand if you're looking at a residential building or a commercial building, and I'll go over the differences there. Then we'll go through an example of a residential unit and a commercial unit and determine the electrical demand for those. And once we go through the example for the residential and commercial units, you'll see what the differences are in calculating the electrical demand for each of those things. Okay, so I just want to go over some basic formulas. So the first is voltage is equal to IR, where V is voltage, I is the current in the units of amps, right? Which is represented by A, and resistance, which is represented in ohms, and this is the symbol for ohms. So when we want to calculate the power, that formula is right here. Power is equal to voltage times the current. And the power can be given in watts here. And the voltage, and you have I, which is the currents in amps. Power can also be represented like this, where power is equal to I squared R, or the current squared, times the resistance. To get this, basically, it comes from this formula and this formula. So basically, in this formula right here, we replace the V with this formula. So it's going to be P is equal to I R times I, which then becomes I squared because you have two I's here. And that's how you get this formula. P is equal to I squared R. You can also have it where P is equal to, when you replace the, in this formula here, P can also equal to V squared over R. And you can also get that by combining the formula number 1 with formula number 2 again. So you could just state that I is equal to V over R, right, from this number 1 formula, and replace I into here, and what you'll end up with is P is equal to V squared R. So you can basically have 3 formulas for power. Okay, formula number 2, formula number 3 here, and formula number 4, which is going to be this one here. So let's go through a quick example demonstrating this formula. So in the example, we have a 208 single phase circuit where the amps that it's connected to is to a coffee maker that is drawing 5 amps. So what is the wattage in that case? Well, we just have to use the power formula, where we multiply V times I, and V in this case is 208, and I is 5. So the wattage in this case is 1040 watts, and this will be the power. Okay, in this picture here, which is a separate example, we need to figure out what E is. E is basically just the voltage. So to figure out the voltage, we have the current here is 2 amps, and we have a resistance here of 7 ohms. And again, the 2 amps, because this is the same circuit, so you have the same amps flowing through the entire circuit here. And to get the voltage, we can use formula number 1, and that's going to be equal to V is equal to IR, and I is 2, in this case 2 amps, and R is 7 ohms. So that's going to give you 14 volts. The electrical service voltage is basically varies depending on which region of the world you're in. So in the US and Canada, the common voltages that you will see in a building are 120, 240 volt, single phase, typical in residential units, or 277, 480 volt, three phase, which is typical in commercial buildings. And this is a AC voltage. You can also have DC. AC stands for alternating current, and DC is direct current. So in an AC system, the voltage basically behaves like this down here, where it oscillates up and down to the voltage specified. So basically 120 or 277, which are common ones in the US. And the Hertz, basically this is one cycle, right, up to this point. Okay, this is one cycle, so it's 60 Hertz. So you have 60 of these cycles in 1 second. In other areas, such as South Korea, Philippines, to just name 2 different regions, they use a different voltage, which is 220 volt single phase, and also 380 three phase, and the Hertz is the same as in the US, which is at 60 Hertz. And in some other areas, such as Singapore, South Africa, and Spain, the phase is a little bit higher, it's 230, and then the corresponding three phase is a little bit higher because it's a factor of the single phase voltage. So single phase is higher here than here, so the three phase voltage will be higher here than for here. And the Hertz is at 50. So you can have differing voltages and differing Hertz based on which region of the world that you're in. In this video, I'm going to focus on the electrical characteristics of the US and Canada. So if you look here, this represents a 208 volt single phase, which represented with this symbol like this, is represented in this picture here. So when it states right here 120 slash 240 volt, sometimes this 240 is represented as 208 volts. So usually when we talk about the single phase voltage in the US or Canada, it's going to be represented as either 208 volt single phase or 240 volt single phase. It pretty much means the same thing. And 120 volt here is also the single phase voltage you can have. So when you have a 120 volt, that means that each one of these phases, so if you look at this picture, this black line is 120 volts, and this red line is also 120 volts. So when you compare the voltage from each of those hot legs, you get 208 volts. And if you take one of these hot legs here to a neutral, which is represented by this white line, you have 120 per phase. So from phase to neutral, it's going to be 120 volts. From phase to phase, you're going to get 208 volts single phase. So sometimes you can also have 208 three phase, and that's represented by this picture here. And you could see that there's 3 hot legs here. It's the black, the red, and the blue, and the white is the neutral. So this can also be represented by this graph here and also this picture here. So looking at each one of these, so this is A, so this is phase A, this is phase B, and this is phase C. which, looking at this picture, are represented by each of these lines here. So the black is one phase, the red is another phase, and the blue is another phase. So if we have the three phases, and each one is oscillating at 60 Hertz, since it's an AC voltage, if you have the three phases offset by basically 120 degrees, you're going to get this type of picture down here. So each of these phases are offset by 120 degrees. So if you have 1, 2, and 3, that's going to be 120 3 times, which is 360. So you're going to get basically each one of these offset by 120. So it's going to be 120 here, 120 here, and then 120 here, and then you're back to basically this point right here. So when you have a 208 single phase, it just means that you have two phases alternating next to each other instead of the third phase. So each of these phases will be at 120 volts. And when it's offset, for example, in this picture, if you could just picture two other phases there, let's say the red and the yellow, the difference, okay, at the peak will be 208 volts. So when you have two single phase 120 volts together alternating, then that's the equivalent of a 208 volt single phase. So looking at this picture here, you could see the voltage is listed on the right side. So basically from phase A to neutral, which is right in the middle, we have from here to here 120, and from phase B to neutral we have another 120, and from C to neutral we have 120. So basically each one of these phases is at 120 volt single phase alternating current, okay, which is basically represented down here. And if you were to take the line-to-line voltage or the phase-to-phase voltage, you get 208. Since the phases are offset by 120 degrees, you're going to get a different voltage when you compare it from phase to phase. So each phase to phase is 208. So this is from phase A to B is 208. This is phase A to C. And then from C to B, you have 208. And this picture basically represents a three-phase circuit because we have the three phases A, B, and C. So the formula to get the voltage line to line from the voltage phase to neutral is right here. So voltage line to line is equal to the square root 3 times the voltage of phase. And phase just means the voltage from phase to neutral, which is 120 volts. So let's say you had a single phase 208 system. That means that you only had, let's say, two of these phases. I'm just going to choose A and B. To get the 208, basically all you're doing is using this formula right here. So you have voltage line to line is equal to square root 3 times voltage of phase, which is 120 volts. And that equals to 207.85, which rounds up to 208. And that's the reason why the phase-to-phase voltage is listed as 208 here. So the formula for power in a three-phase circuit is represented by this here. It's actually square root 3 times the volt line to line times the current in the line. So IL represents the current through the line. So it's just each one of these phases here, and the current that flows through is the I line. And for a three-phase system, the formula here is actually the S, which is this part right here. And that's considered the apparent power. The real power is actually the amount of power that is consumed by the equipment. So that's also represented as watts. So the complex power S is represented by VA. And when the equipment uses power, that's actually the real power that it's using, and that's represented by the watts. And the reactive is the third part of that triangle. The main point of this is that the current that is flowing in the wire is going to be represented by this VA. So you can have, let's say, 100 amps flowing through, and the motor, let's say all of this is attached to a motor on this side, okay? So let's say you have 100 amps, and let's say 50 amps is being used by the motor. So that means that the 50 amps will contribute to this wattage value here, since that's the real power, or the power that the equipment is using. So in that case, you have 100 amps flowing through the line. 50 of it, or half of it, is being used by the equipment. So just because you have a certain amount of amps that are flowing through this, it doesn't mean that 100% of this is going to be used up by the equipment. Okay, so when we look at this formula here, you can see that it's square root 3 voltage line to line I line. So voltage line to line is equal to this right here. So once you replace that into the V line, you get square root 3 times square root 3 VP IL. These two square root 3's will cancel out to just a 3 VP IL. And VP is the voltage of the phase. In this case, it's 120. So it's 3 times 120 IL, or 360 IL. So a quick way to get the power of a three-phase circuit is to just multiply the current times 360 to get the apparent power, or the VA. So in this example here, let's say you have a 208 three-phase motor, and the full load amps of the motor is 2 amps. That means that 2 amps is flowing through each of the phases in this alternating type of pattern here. So what is the wattage? Well, the question is, what is the VA actually? Okay, we want to get the actual current that's flowing through the line, which is the apparent power, or the VA. So to get that, we basically take 360 times the current of 2. That comes out to 720 VA, and this is the apparent power. Another point I want to mention is when you see this type of voltage written in this way, where it's 120/240 volts single phase, that means that it's actually this type of setup here, where you have the 120 here, right, and the other 120 volt phase here, and together from line to line, this makes the 208 volt single phase. And each one of these 120 volt single phase lines to the neutral, which is this white line here, makes the 120 volt single phase of this panel. And this type of service is represented like this: 120/240 volt single phase. All right, so we're gonna go over the basic electrical service for a residential house. So you have this transformer. So this is the power from the utility company. Typically this is at a higher voltage, okay, than this transformer. So let's say this transformer is converting it to 120 volt 208, or in other words 240 volt single phase. And the voltage on the Con Ed side, from my understanding, is a very high voltage, such as 13 kilovolts, so 13,000 volts, 27 or 33 are the standard voltages that I'm aware that Con Ed provides at the service. But for most of the electrical design work, we only concern ourselves after the transformer and the voltage that is supplied to the building itself. So we're not concerned about the voltage that the utility company provides. We're only concerned about the voltage that goes into the building. So we have a couple of components. So after the transformer, it goes through this service wire to this head here, which is called the weather head, and this is the service mast here. So this is the weather head and this is the service mast, and you can see here the splices that basically connect the wires. And then as soon as it goes down the service mast, it goes into the meter. Okay, in this picture you'll see the meter here. So the service comes in and the meter is here, and then from the meter it goes to the main disconnect switch, then to the building. Inside the meter it looks like this. So in here you could see there's one hot leg, another hot leg, and this looks like the neutral here. So this would be a 120/208 volt single phase service right here. And then it will basically go through and then it goes into the disconnect. So you can see that the hot legs, the neutral, all go into this disconnect, and this would be the switch that sends power into the building. Okay, we have another picture of that same thing. So we have the meter right here, and the one hot leg here, the other 120 volt hot leg here, and the neutral, and then they all go through into this main disconnect switch. And the switch only switches the hot legs. The neutral is not switched, as you can see here. It's just a metal bar here that basically has a main bonding jumper that is typically a green screw that's going to make a connection, a solid connection from this bar, this neutral bar, to the metal frame of the main disconnect. And then you also have a grounding conductor here that typically goes into the ground, or it could go to a metal beam inside the building. Okay, and this basically grounds the whole system. And then all of this then goes into your panel board. Okay, and this is the hot leg that goes through, and the other hot leg that goes through. And each of these circuit breaker slots would then connect to the two phases in alternating sequence. So the first one, let's say this is phase A, this is phase B. The first one would go to A, second one will go to B, and then it would continue that alternation. So if you look at a schedule, a panel schedule, such as this would be representative of a 120/208 volt single phase, where you have the two phases here, and then one phase to the neutral would make the 120 volt portion of this type of service. And you could see the first row is connected to phase A, including this side as well. And then the next row will be connected to the other phase right here. And then it would alternate between the phases as you go down the rows. Also, you could see that the numbers are odd on the left side and even on the right side. So the circuit number goes from 1, 3, so on the left, and the circuit numbers are 2, 4, and so on the right side of the panel schedule. Okay, now that we have a basic understanding of the electrical formulas needed to do the electrical load calculation and some of the basic components of a electrical service layout into a residential building, We're going to now go through the NEC calculation method to calculate the feeder size for a residential building. And those are covered by Article 220 of the NEC in 2008, which is the current code during the time of this video. And you would have to follow your current code at the time of your project. The table 220.12 will give you the requirements for general lighting and receptacle loads. And table 220.42 will give you the demand factors that you could apply. Okay, so if you look at 220.12, this is the general lighting load, okay, by the occupancy type. So you can see the various occupancy types and the unit. And in this case, we don't use meters. We're in the US where we use foot. So it's going to be volt amperes, or the apparent power per square foot. And you can see the various occupancy types. We're only going to focus on the residential for now. And for residential units, it's called dwelling units. So for the dwelling units, we have to use 3 volt amperes per square foot. And that will be the general lighting. And in the NEC, they state that you can also include the general receptacle load into this value here of 3. So this 3 times the square foot of the residential unit would account for the general lighting and the receptacle load for that dwelling unit. Then you can apply a demand factor using table 220.42, which is this here. So for dwelling units, you would follow these rules here. And for different occupancy types listed here, you would follow different demand factors. And you can see here, for all others, such as commercial buildings, which we will cover later in this video, we have to take 100%. So basically, no demand factor in that case. We have to use the full load. So for dwelling units, you have the first 3,000 or less, you would take the full 3,000 volt amperes. Then the portion after the 3,000, so let's say you have 5,000, that means that 2,000, which is the remaining after the first 3,000, would get a demand factor of 35. And then over 120,000, you would take that as 25%. And the reason for that is because NEC believes that typically for the volt amperes to exceed that first 3,000, it's not going to happen very frequently. So then that's why you get these demand factors that can be applied. So you don't use the full 100% load of that. And then as it gets even higher, NEC believes that even less of that portion would be used, and that's why you take a demand factor of 25% of anything over that 120,000 volt amperes. Then next, for the calculation for residential units, you would have to add for each laundry room 1,500 volt amperes, and you would apply a demand factor of 75% for 4 or more appliances other than the cooking electric range, the clothes dryer, and the heating or air conditioning equipment, because all of these will be added somewhere else in the calculation. For the electric clothes dryer, you would use 5,000 watts. So sometimes you can have a gas clothes dryer or an electric. So whenever you have an electric, typically you could just use 5,000 watts. If the actual electric clothes dryer uses more than 5,000, then you would have to use the higher value. But usually 5,000 is the higher number, so you would just use 5,000 watts for each electric clothes dryer. And for residential kitchen equipment over 1.75 kilowatts or 1,750 watts, to be based on table 220.55, which is right here. So based on the number of appliances you have, you can apply a demand factor based on the kilowatt rating of that equipment. So sometimes you can have an induction cooktop where it draws a lot of wattage. And in that case, based on the wattage, so let's say we had 5 kW of cooking, it would fall under this column here, okay, which is between 3.5 and this 8.75 kilowatt rating. And based on the number of those appliances, you can apply a demand factor of it. Because NEC believes that the full capacity of all the cooking won't be used at any one given time. We also need to add, for the residential calculation, the non-coincident load. And this basically means that loads that will not be used simultaneously, and usually that's from the HVAC system. So you can either have cooling or heating typically in a building. It's never both unless you're in like a large building where you might need all your cooling for like an IT room, right, during the winter time. But typically for a residential, you either have the cooling system on or the heating system on. So that would be considered a non-coincident load. And in that case, you only have to pick the higher of the two loads when calculating the feeder size. Because if you add both, they're oversizing the feeder. So you basically do that to add the non-coincident load. And after that, you would have to add 25% of the largest motor load. The reason for that 25% increase of the largest motor load is because when a motor starts, the current is higher at the beginning than when it runs at steady state. So if this is the x-axis, I'm going to put the current on that x-axis and time on the y-axis. When the motor starts at time 0, the current is going to be a lot higher, and then it goes like this. Okay, where this line would be the full load current of the motor, and this right here would be the starting or inrush current, or in other words, the locked rotor current of the motor. And typically, the locked rotor current is about 7 times the full load current of a motor, but that could vary based on the motor. My understanding is it's about 7 times the full load current. So that's the reason for this 25% increase of the feeder size.